All right. So last time, what we found was when we had some data that, so we had like, W0 and W1, W2 and W3. When we had data where each time we added a constant, 2.2, then it turns out we could find a solution function, and W as a function of m was 2.2m plus 7. Okay. And in fact, anytime you have data that behaves in this way, and what I mean by behaves in this way, so we have t, and then we have like whatever we're measuring, so I'll just call it m sub t, and here you get some number, and then, maybe I have to add some constant to get the next one. So whatever number I started with, you know what, we have a name for this number. Let's just use the notation. This number, my starting value, my initial condition, which is a word I did not say last time, initial condition, which just means your first measurement, okay, your starting point. First measurement, or your starting point. Okay, you get it. So maybe, to progress, it turns out that m1, well, that was actually just equal to m0 plus c. And maybe that phenomena continues. So m2 is just m1 plus c, and so on and so on. Okay, so in other words, my difference equation is something like m sub t plus 1 minus m sub t is a constant. Okay. Well, then we can find the solution function for this by doing that weird process I talked about last time, where I want to find these values, m0, m1, m2, and then also m3. I want to find them by just kind of continuing to do stuff to m0. So let's do that. So right here, well, okay, first off, going into m1, I did something to m0, I added c. Going into m2, instead of writing m1 plus c, let's get rid of that, I want to only use m0 and arithmetic. So instead of writing m1, I write m0 plus c. But then I also have to add c, because that's the update to go from the second row to the third. Similarly, if I update again, then I take the previous measurement and I add c. So my previous measurement was m0 plus 2c, and then I add c. And what we find is that if you tell me a t value, I can tell you what's going to go in this slot, my m sub t. It's going to be m0 plus t many copies of c, plus tc. So this all might seem too abstract just because I'm only using variable names. But this is to say that my solution function is a line. It looks like a slope times my independent variable plus my y-intercept, or my initial condition. Okay. And when you have a solution function, instead of writing m subscript t, you can also write m of t, but I'll just continue to write it as m subscript t. Okay. So this is just, we now have this really powerful thing. Anytime we have this add a constant type of difference equation, that means our solution function looks like that constant is the slope, and then we have this equation of a line. Let me say this differently, okay? And we're actually going to do something a little bit more powerful. Okay. So, all right. So I'm going to restate the last thing, but just in a new way. So suppose we're monitoring something. Okay, maybe it's the length of an insect every single day, or the height of a tree every single month, or something like that. So some length, and it's some function of time. Okay. and it's linear in time. So it looks like mx plus b, in this case mt plus b. Suppose that's true, but we didn't know it, but unknown. Okay. So we take data, so we measure. Okay, and this represents the length of something, that's why I used L. But anyway, so we measure. So the measurements we get, we find out that at time 0 we had b, and at time 1 we have m plus b, and at time 2 we have 2m plus b, and at time 3 we have 3m plus b, and so on. Okay? And so if we're doing these measurements, then based on what I've been labeling before, we would call this t, and we would call this L subscript t. Now, I guess earlier I've been using capital letters, so if you'd prefer, I could just call this capital L, but whatever, it's the length of something. And we stare at this data and we go, hey, wait a second, I added m, I added m, I added m. Well, let's actually just kind of make that more official. And in this next column here, I'm going to compute L sub t plus 1 minus L sub t. In other words, right, I might look at L sub 1 minus L sub 0, and that would give me m. Or I might look at L sub 2 minus L sub 1, and that will get me m. Or I might look at L sub 3 minus L sub 2, and that will get me m. And so this column here is something I'm going to call the first difference. When our first difference is constant, that is the data trying to tell us the solution function is linear. Okay? When the first difference is constant, that means the solution function is linear. Let's look at another thing. Okay, suppose, in fact, it's the exact same setup. We're going to measure some kind of population as a function of time, and this population looks like at squared plus bt plus c. So a, b, and c, they're all constants. But we don't know this, okay? How did I write it last time? Is true but unknown. Okay, suppose this, but unknown to us. So we measure. So we measure. And we get data on this population. So we find out at time 0, that population was C. And at time 1, that population is A plus B plus C. A plus B plus C. And at time 2, so all I'm doing is I'm going to plug in 2 for my T. Okay. And what I get is 4A plus 2B plus C. Let's do it again. At time 3, I have 9A plus 3B plus C. And at time 4, I have 16A plus 4B plus C. Okay, and we could continue to collect data, right? And then I'm trying to figure out the difference equation, or the updating function. So I look at the first difference. I look at P sub t plus 1 minus P sub t. So I have to take this entry minus this entry. Okay, I have A plus B. Let's just use a different color, just to kind of have A plus B. And then I have to take this entry minus this entry. So let's see, the C's cancel. 2B minus B, I'm just left with 1B plus. And then I have 4A minus A, I have 3 A's. Okay, let's do it again. So now the C's cancel, C and C, they're gone. 3B minus 2B, I'm left with 1B. 9A minus 4A, I'm left with 5 A's. And one more time, the C's cancel. 4B minus 3B, I have a B. 16A minus 9A, I'm left with 7 A's. Okay. So we would find no longer is our first difference constant, right? These are changing. Here, if you prefer, let's carry this out with an actual, let's just pretend p of t was 3t squared plus 2t plus 1. Okay. Then if I were to fill out this table, I'll go up here. I have t, I have pt, and then I'm going to do the first difference. Okay, I'm getting a little bit tired of writing this here, so I'm just going to use triangle pt. Okay, triangle, it's pretty common for that to mean the change of. So this is the change of pt. So the first difference, so that's going to go over here. Triangle pt. And when I plug in 0, I get 1. When I plug in 1, I have 3 plus 2 plus 1 is 6. When I plug in 2, oh, gross. Let's see. Let's just, well, okay, fine. So when I plug in 2 into t, then I have 3 times 4 is 12, plus 2 times 2, so 12 plus 4 is 16, plus 1 is 17. Okay. When I plug in 3, I have 9 so 27, plus 6 makes it 33, plus 1 is 34. And that's probably good enough. So now let's do the first difference. So I do 6 minus 1 is 5. 17 minus 6 is 11. 34 minus 17 is 17. And okay, let's do one more. Let's go ahead and plug in 4. So we're plugging 4 at 3 times 16 plus 8 plus 1. 3 times 16, let's see, we have 30 is 48. 48 plus 9 is 57. Okay, 57. And 57 minus 34, let's see, I guess that'd be 23. Okay, 23. All right. So in this case, right, we don't have a constant first difference. We don't have a constant difference equation. We don't have a, well, anyway. But if we do the difference algorithm again, so to get this 5, I did 6 minus 1. To get the 11, I did 17 minus 6, and then 34 minus 17, and then 57 minus 34. Let's do that same idea again. 11 minus 5. What do we get? 6. Okay. 17 minus 11. What do we get? 6. 23 minus 17. What do we get? 6. Okay. So the second difference, whatever the heck that means, which I'm just going to use del squared pt, this time it's constant. Okay. It's not a coincidence that when we have an underlying natural phenomena, which is measured by a quadratic, or which is quadratic, I should say, not measured by, when it is quadratic, our second difference is constant. That is the data trying to tell us the way the variable being measured behaves. Similarly here, when our first difference was constant, that was nature trying to tell us we had a linear thing. In general, if you repeat this difference, right? So let's say you just have a bunch of data, okay, tons and tons and tons of data, and then you do this difference algorithm, and you get something that's, oh, sorry, you do this difference algorithm, and you get something that's not constant. You do it again, and in this case I got something constant. Oh, okay, so I'm degree 2. But maybe it's not constant again, so then you do it again, and you do it again, and you do, right? Eventually, if you get constants, that is the data telling you what your solution function is going to be like. Okay, but that's going above and beyond this course. Part of why I want to let you know that is, well, this is something that was known to ancient mathematicians because they cared a lot about quadratics and trying to find like perfect squares and things like this. Or not perfect squares, but Pythagorean triples and things like that. They cared about quadratics. And so really, like, let's just, if I were to plug in t plus 1, so this is sort of like, you should think of this as p sub t plus 1, it's like the next measurement. If I plug this into this equation here, I have a t plus 1 squared plus b t plus 1 plus c, and I can work this out a little bit. So first off, t plus 1 squared, that's t squared plus 2t plus 1. And so if I distribute an A in there, then that's what I would get. So I'm going to go ahead and just jump to writing that down here. So I have AT squared plus 2AT plus A plus, now I have to do this one, so I distribute the B. I have BT plus B plus C. Okay. Now a first difference, a computation of P sub T plus 1 minus P sub T, means I would take this monster, that's my P sub T plus 1, and I would subtract P sub T. So let's do that. And since I have the technology in my hands, I can kind of move this on down, and I can say, okay, this is equal to this monster minus P sub T, which is AT squared plus BT plus C. All right. So my first difference is that minus that, and what do we get? What do we get? Let's see, the AT squares cancel. I have a 2AT plus, okay, BT's cancel, C's cancel. I guess I'm just left with, let's see, so taking care of that, I have an A, okay, so plus A plus B. All right, so this is linear, right? My variable, my independent variable is T, so there's just a number times T plus another number. It kind of looks like MT plus B. B was already used, plus some constant. C was already used. It looks like mx plus b. It looks like a line. It's linear. And this is a phenomenon we're going to see again much later in this course, which is that the derivative of a degree 2 polynomial is a degree 1 polynomial. Anyway, I just want to show that to you now. And right, to a historical note, let's look at a discrete time dynamical system where we're going to track the position of a falling ball. And we might be tempted to use the bottom line of the ball, but I got this by snagging a bunch of freeze frames on YouTube, and it gets kind of blurry, and the data works out much better if you just use this dark spot on the ball. Okay, so I'm almost going to be rounding a bit just to make my life easier. Okay, so this ball is falling, and at 50 milliseconds, we snap this photo, and we find that it has fallen 1 centimeter. These are in centimeters. Okay, that's what it tells me. All right, and the next 50 milliseconds go by, we snap another photo, and now the dark spot is here, and I'm just going to say it's between 4 and 5, so I'll just say it's at negative 4.5. Okay. All right, another 50 milliseconds go by. I'm going to say I'm at negative 10.5, right? Again, here's that dark spot that I care about. All right. Oh, the dark spot's basically right on that line, so negative 19. That looks pretty good. All right, where are you? Here you are. Yeah, you're basically at negative 30. Okay, let's put that data in a table. Boom. So the position of my ball is a function of time, and time 0, I'm 0. That I did not show. It's a very boring frame. The next frame, so frame 1, the first thing that I've given you a picture of, I'm at negative 1 centimeter. Frame 2, I'm at negative 1.3, right? But time is being measured in 50 millisecond chunks, so you could also think of it like that. This should be 150, but okay, I got lazy. Anyway. All right, so I have this position of a ball as a function of time, and it's falling. And now I do the first difference. Okay, I do this first difference. And I find, okay, subtract 1, subtract 3.5, subtract 6, subtract 8.5, subtract 11. And that doesn't help me too much. But if I do a second difference, I get constants. Okay, this is the data trying to tell me that the position of a ball as a function of time is a quadratic. It's AT squared plus BT plus, oops, not 1, but C. Okay? And we could work out what these constants should be. And in fact, if you do that, then you basically have an estimate for the acceleration due to gravity, because it turns out whatever this little a is, it's like the acceleration due to gravity over 2. Okay. Anyway, so I just want to give you that example. A challenge question, and then we'll go to stuff more applicable, would be, so this yellow dot is growing, right? And I should really call this step 0, and then 1, and then 2. Okay. And I want to model the area, and let's say that this happens like every single second. Okay, 1 second, 1 second. area as a function of time. And so can we come up with so what is this? This is the area after t seconds. Okay, so the area after 0 seconds is 1. Area after 1 second is, let's see, 1, 2, 3, 4, 5, 6, 7. Area after 2 seconds, oh gosh. Okay, so here's the 7 that I just did. So I just need to count this new stuff. And it looks like there's 12 new ones, so I have 19. Okay, if you continue this process, what would A3 be? What would A4 be? What would A5 be? And then play with this a little bit. Use this this first difference, second difference method. See if you can figure out a solution function. See if you can find A of t. So my input is t, and then my output is the area. If not, okay, that's fine. Can you find a difference equation? A difference equation. So we need to do a sub t plus 1 minus a sub t. And I'll tell you what the answer is, just not leave you hanging. It's 6 times t plus 1. So anyway, that is a challenge exercise. If you would like me to post the solution to it, then comment, or just, you can email me. You're in the class. All right, next time we will talk more about population growth. The only solution function that we're going to be required to know for this class, well, there's 2 types. One we're going to talk about next time. The other is the linear one. So you're not going to have to do this really tricky quadratic stuff. I just think it's interesting to know. But you will have to do the stuff outlined in the first video. So that type of solution function might come up in your future. Okay, we'll pick it up next time.